What's going on, everybody? This is Mr. Diamond, and in the last video we talked about sigfigs. We described how we figure out which numbers are significant. We did these example problems together, and I don't think I actually showed you this underlined part, but we figured them all out, and hopefully you're feeling a little comfortable with the rules. And you may be going, okay, well, if we know how many digits are significant, why does that really matter? What does that help us do? And the reason we need to be able to do that is because when you are using a calculation in this class, you have to give your answer based on the sigfigs of the numbers you were given. There's two sets of rules for rounding your answers in problems, as well as one for one for addition and one for multiplication, and they're kind of subcategories. So adding, subtracting have their own set of rules. Multiplication and division have their own set of rules. First thing we're going to start with, though, is when you round your numbers in this class, you will never be told to do decimal places or to 3 decimal places or something like that, like in your math class. And you'll never be expected to give a really long, super lengthy answer that's like 15 decimal places or anything like that. Your answer will be based on the sigfigs of the number you used to calculate that number. The first piece that we care about, though, just to make sure we're all on the same page, is that when you're rounding a number, we start with the same basic rules as you've probably learned for a long time ago and have been using a lot of your life. If the first digit you drop is 4 or less, you keep the last digit the same. So 94, if you round it to the tens place, you would round it to 90. If the first digit is 5 or greater, increase the last kept digit by 1. So if it's 96, you would up it to 100. That would be to the nearest tens place. Same as the rules you've probably been using your whole life. Now, for the next piece, though, it gets a little bit weirder. When you're doing multiplication and division problems, your answer needs to have the same number of sigfigs as the lowest amount of sigfigs used in your calculation. Now, why is that? Why do we do that? What is that doing for us? Well, we talked about in the last section about how measuring information in science, you are allowed to report your information to one step beyond what your device could actually read. And by making it so that your calculations are tied to your lowest possible accuracy value, your thing that was measured with a tool that did the worst, we're basically giving your problem the most, like, it's not really like benefit, because it's almost the opposite of benefit, but we're basically saying, like, you have to be precise and good on your measurements with everything you do. If you slack in one area, your whole rest of your calculation and your answer will suffer because of that. We don't want people measuring to like the tens decimal places, and then using like a ruler to measure the last piece. Or someone who's measuring down to like the micrometer, and they're measuring the microgram, and then they're measuring the thermometer with like just like a household thermometer that only goes to 1 decimal place. Like, if you are measuring things to a very, very small amount, like let's say going down to 4 decimal places like we do in this example here, but one of your tools just doesn't go that far, that's your problem for using a crappy tool, and your answer will suffer because of it. It's not fair. It's really easy to mislead someone in theory if you're using one number that's like really badly measured and the rest of them are all very, very accurately measured. So scientists have agreed that you are only allowed to report your answer to the accuracy of your least accurate answer. So in this case, 24.65 times 0.67 equals 16.5155. That's what you would get if you plug it in your calculator. I think it's exact. Don't quote me on that. But you would then look at your numbers and you would say 24.65. All of those are significant. That's 4 sigfigs. Go over here, that 0 is at the beginning, so it's not significant. So 6, 7, that's 2 sigfigs, which means the answer you would report here is actually the first 1 is significant, the second 6 would be significant. I usually draw a little squiggly line right here, and I go, okay, that's 2 sigfigs. Now I round at that position. So I have to keep these 2 digits. I just round based on there. If this is a 5, I round up. So my answer would then go to 17. And that may feel weird because these are like 2 decimals, and obviously we got a longer decimal number. Like, most people's instincts would be, I'll just say 16.5. But no, based on the sigfigs, because this number was measured so much more accurately than this number, we have to use this number as the basis for our answer, how many digits we give it to. This one was 4, sure, but this one sucked. This one was only 2. Our answer has to go to 2. Going the other one, we have another example, but kind of going the other direction. We had one tool that measured us 8.00. We had another tool that measured us 2.00. So both of those are to 3 sig figs. Those zeros are at the end of the number and after the decimal. So our answer when you plug that in your calculator is 4. However, we need to report our answer to the lowest number of sig figs, which means even though our answer in our calculator is 4, we actually have to add things to that to make it more significant. Now, we can't just add zeros because for one, that's going to make it into 40 and 400 and 4,000 and stuff like that. And those zeros wouldn't be significant anyway. So instead of just being 4, we're actually going to do 4.00. Again, I said you can't willy-nilly add zeros, but if you need to increase the significance of your answer, you can actually go back in and add zeros because your answer in this case is not about 4. Your answer would be exactly 4. You got 4.00 to 2 digits of specificity, knowing that those would also be zeros. So this is how we round with multiplication and division. Now, what about addition, subtraction? We said they have their own rules. In addition and subtraction, you don't actually care about sig figs, really. We care about decimal places. Decimal places are more important because when you're dealing with numbers that are adding and subtracting, we're more concerned that the values are close to each other in decimal values as opposed to numbers being the same amount of significant figures. Like 1,000 compared to 1, like they have the same number of sig figs, but like it just is a little bit easier to kind of consider them as decimals. We're not usually radically changing the numbers. So instead, in our example here, we have 2.367 plus 34.1. This number was measured to 3 decimal places of significance, and this one was measured to 1 decimal place of significance at the end. Now, yeah, this has 4 sig figs. Yeah, this has 3 sig figs. But what we really care about is this number measured really, really well and measured down to a very, very high amount of decimal places for specificity, whereas this one only went to 1 decimal place. Since we're not multiplying and dividing them, we don't really care about the total number. We just care about, well, how accurate were both of our tools? And in this case, this tool was way less accurate. So we're actually going to have to take this number and go only to 1 decimal place because that's the lowest amount of decimal places as any of our answer had. Again, we have to base it off of our worst number. Your answers are based on your worst calculation or worst measured value that you had. So if I go to 1 decimal place, I get 4 is the number right in front of it. This is a 6, which means I round up, so it'd be 36.5. And if I go to this other one, 255 minus 175.65, you would get 79.35, but this has no decimal places. This one has 2. Same situation as that last time. This one was measured pretty accurately. It went to 5 sig figs of measurement, 2 of which were decimal places. In this case, I measured to 3 sig figs, but none of them were decimal places, meaning that this tool was not nearly as accurate as this one. So we have to cut back our value by quite a bit, and we actually have to round our answer to no decimal places. So it's 79, we'll cut off there. 3 means we round down. You don't really round down, you keep the same. So it would be 79 as your answer for that one. So those are our rules. Addition and subtraction based on lowest decimal place of a number used. Multiplication, division based on lowest number of sig figs that you used in the problem. All right, that is our sig fig rules. You're going to have a big old worksheet that has all these types of questions: addition, subtraction, multiplication, division, and just determining basic number of sig figs. We'll work on that for at least a day in class. It's definitely something you'll want a lot of practice with because we're going to be using it a lot this year. So if you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.